Did you know there are stars so dense and compact that a single teaspoon of their material would weigh billions of tons? No, this isn't science fiction. These are neutron stars, and they're among the most extreme and fascinating objects in the universe. Imagine something the size of a city weighing more than Mount Everest. How is that possible? These stars can spin hundreds of times per second, emitting signals so precise they're like cosmic clocks. And the most incredible part, they might even help us unravel the secrets of space-time. Want to know how something so small can hold such colossal forces? Let's explore the mysteries of neutron stars right now. What are neutron stars? Think of a massive star much bigger than the sun. When it reaches the end of its life and no longer has enough energy to stay stable, a gigantic explosion called a supernova occurs. This explosion hurls much of the star's matter into space. But the core, the central part, doesn't disappear. Instead, it's compressed so extremely that it becomes a neutron star. It's as if all the remaining mass of the star is crushed into something as small as a city. That's why they're super compact. Even though they're much smaller than the Sun or Earth, neutron stars have such high density that it's almost unimaginable. If you scooped up a teaspoon of a neutron star, it would weigh billions of tons. That's why neutron stars are so special. They're the remnants of giant stars that went through an incredibly violent and awe-inspiring process, leaving behind these tiny, yet insanely heavy balls of matter. Why are they so heavy? The big question is, how can something so small be so heavy? Let's imagine this. You take a soccer ball and compress it, squeezing and squeezing until it's the size of a marble. Even though it's smaller, the weight stays the same because you didn't remove any material, just packed it tighter. With neutron stars, the process is similar, but on a much grander scale. The gravity is so intense when a star collapses that it crushes all the core's matter into a super tiny space. And because of that, the weight that was once spread across a huge star is now concentrated in an area the size of a small city. The most amazing thing is that this density creates immense gravity. If you were near one, you'd feel a pull so strong that nothing could escape. It's as if all the weight and power of a giant star were gathered there in that tiny space. That's why, despite being so compact, a neutron star weighs millions of times more than the entire Earth. What are they made of? Normally, the things we see and touch are made of atoms, which have protons, electrons, and neutrons. In a neutron star, what happens is that when the giant star collapses, the pressure becomes so insane that electrons and protons merge, forming a sea of neutrons. These neutrons get so packed together that there are no empty spaces like in normal atoms. It's as if the material is compressed to the absolute maximum, creating something unlike anything we know on Earth. The surface of a neutron star might be solid, but it's incredibly hard and dense. Just below, the material turns into a strange fluid where the neutrons are so close they almost act like a single substance. And the deeper you go, the weirder the matter gets. Some scientists believe that at the core of a neutron star, there might be a state of matter we don't find anywhere else, like a soup of subatomic particles or even something called quark matter. It's fascinating because these stars are like natural labs for studying the universe under extreme conditions. How do we study these stars? We can't visit a neutron star, of course. They're far too distant from Earth, in regions of space that would take us thousands of years to reach with any current spacecraft. So how do we know so much about them? The answer lies in the light and waves they emit. Even though we can't see them with the naked eye, telescopes and observatories capture the signals coming from these stars. X-rays, radio waves, and even flashes of visible light in some cases. Some neutron stars spin really fast, emitting steady beams of radiation. These beams, when they sweep past Earth, create regular pulses like a lighthouse. These are called pulsars. By studying these pulses and other types of radiation, scientists can calculate things like the star's density, magnetic field, and rotation speed. And when we put all this data together, we can build a model of what they're like and even what they might be made of. It's like hearing a sound from far away and figuring out who's making it and how based on its pitch and rhythm. What's the difference between them and black holes? When a giant star dies, two things can happen depending on its mass. If the core is too heavy, gravity wins completely and the star collapses into a black hole. That means it's so dense, it forms a kind of abyss in space-time, from which not even light can escape. That's why we can't see black holes directly. Neutron stars are a step before that. They're so dense, they're right on the edge of becoming a black hole, but they still manage to resist that extreme gravity. It's like they're fighting against this force, using the insane pressure from the crushed neutrons. In other words, a neutron star is a delicate balance. Gravity tries to make it collapse completely, but the quantum pressure of the neutrons holds it back. So, while black holes are invisible and swallow everything around them, neutron stars are like cosmic survivors. We can still detect them because they emit light and other signals, unlike black holes, which we only observe through their effects on the surrounding environment. This makes neutron stars a unique class of space objects, mysterious and captivating. They can spin really fast. One of the most striking features of neutron stars is how fast they spin. When a normal star collapses into a neutron star, all the rotational motion it had gets concentrated into a much smaller space. It's similar to what happens when an ice skater pulls their arms in during a spin. They spin much faster because the weight is closer to the center. This effect causes some neutron stars to spin hundreds, sometimes thousands of times per second. The fastest ones are called millisecond pulsars because their light pulses are so frequent they happen in fractions of a second. It's almost like watching a light blinking non-stop at super high speed. For scientists, this extreme spinning is an incredible opportunity. Studying pulsars lets us learn more about the physics of these objects, how their magnetic forces work, and how they interact with nearby material. Plus, these rapid spins are so precise that some neutron stars act almost like cosmic clocks, helping astronomers measure time and study the very structure of space. Why are they fascinating? Neutron stars capture the imagination of scientists and curious minds because they represent one of the universe's extremes. They defy common logic, small as a city, yet incredibly heavy, dense, and fast. They show us how the cosmos is far stranger and more complex than we can imagine. Plus, studying neutron stars is like peering into a natural laboratory where the laws of physics are pushed to their limits. Here on Earth, we can't recreate the extreme conditions inside these objects. So by analyzing them, we learn more about matter, gravity, and even how space and time behave. And the most amazing thing is that these stars aren't just an isolated mystery. They also help tell the story of stellar evolution, showing what happens after a star dies. For all these reasons, neutron stars aren't just cosmic giants in a physical sense, they're also giants in terms of the knowledge they bring us. Their role in the universe. Beyond their incredible density, spin speed, and composition, neutron stars also play a big role in the cosmos. For example, they help spread heavy chemical elements across space. When a star explodes as a supernova, the materials from its core and surroundings are flung in all directions. These elements can later become part of new stars, planets, and even life. Neutron stars are also key to studying phenomena like gravitational waves. When two neutron stars collide, the energy released is massive and creates ripples in the fabric of space-time. These events are rare, but when they happen, they give scientists a chance to study gravity on a level that was previously impossible. So, even though they might seem like tiny dots in a vast universe, neutron stars have a disproportionate impact. They don't just teach us more about physics, they also help build and shape the very universe we live in.